Hi, I'm Preston Putzel from University of California, Irvine, and I'm presenting on our work on dynamic survival analysis for EHR data with personalized parametric distributions. Our paper focuses on dynamic survival analysis with EHR data, and our task of interest is making up-to-date and personalized time-to-event density predictions using the EHR data of an individual, shown here on the left, to make the individualized predictions shown here on the right. To make these individualized predictions, we split our model into two parts. The first is a parametric global density representing the average density of time to event across all individuals. Given this global density, our model then learns a mapping from each individual's EHR data to effective times located within this global density shown here in different colors. Given these effective times, we get individualized densities by truncating and renormalizing the global distribution at the effective times. Notice the individual here in red represents a patient with better risk, perhaps with good blood pressure and a stable, healthy temperature, while the individual in blue represents a patient with a higher risk of an adverse health event, perhaps with a very severe fever. So in short, our model learns a function from the covariate history of each individual to these locations, which represent the effective time of an individual if they were to have the similar risk as the average patient at that time. We also propose a new form of the dynamic C-index. Consider predicting time to onset of cardiovascular disease, like in one of the dataset applications in our paper, with each of the hearts here representing different times to events for different individuals. The three individuals to the left represent individuals who have already had CVD diagnosis, while those to the right are still at risk at the present time. Then a commonly used dynamic C-index for evaluating survival machine learning models evaluates performance over both at-risk and non-at-risk individuals, whereas our proposed version only evaluates performance over at-risk individuals, which is more relevant for clinical applications of a model. We also apply our model to a COVID-19 dataset containing labs, vitals, medication usages, with predicting time until severe COVID onset as the goal. For this application, as well as others, our model is competitive with more complex modeling architectures, such as dynamic DeepPet on the at-risk C-index, and it also outperforms more classical survival methods, such as a landmarked Cox proportional hazards model. The main results from our work are that combining machine learning optimization techniques with simple parametric densities yields competitive performance with deeper machine learning-based models, plus easier interpretation of results. Also, that models must be rigorously evaluated in a way that matches their possible clinical use case. For additional details, please visit our poster, where we discuss results in more dataset, additional comparisons of metrics, and additional discussion of different models and the trade-offs thereof. Thank you.